Hello, my name is Isaac. I'm a tutor at CWI, and today we're going to be working through practice exam problem 3 from practice exam 2 for physics 212. And the question is it feasible to construct an air-filled parallel plate capacitor that has two plates separated by 0.1 millimeter and a capacitance of 1 farad? Why or why not? Alright, so the first thing to look at is how do we calculate capacitance using physical parameters for a parallel plate capacitor. And that's this equation right here. Capacitance equals the permittivity of free space times the area of one of the panels of the parallel plate capacitor divided by the distance between them. And we were given the distance in the problem. It's 0.1 millimeter. So the distance is 0.1 times 10 to the minus 3 meters. I'm just going to convert that to meters right away. And we know that the capacitance that we're looking for is 1 farad. And now the question is, what would be the area? And see if that's feasible. One thing to note is that the permittivity of free space, E sub 0, stands for the permittivity in a vacuum. Now, air is extremely close to a vacuum, so remember there's a different epsilon value for different substances, but what we're going to say in this problem is that E sub air, or the permittivity of air, is approximately equal to the permittivity of free space. So we can still use this equation using the permittivity of free space value. Alright, so let's set it up and write in what we know. So we don't know area, so that's kind of what we're solving for. So let's go ahead and rearrange this equation by multiplying d over and then dividing by E0 and rearranging this to solve for area, which is our unknown. We know that C is going to be 1 farad. The distance we were given is 0.1 times 10 to the minus 3 meters divided by E0, which is 8.85 times 10 to the minus 12. And that's going to give us our area in square meters. Alright, so let's plug it in. And what we get is 0.0113 roughly times 10 to the minus 3 plus 12 times 10 to the 9, and that's meters squared. So now that we know area, well, first let's move our decimal 2 places to give us 1.13 times 10 to the 7 meters squared. I believe that's right. We're making it look bigger, so we have to make the exponent smaller. So that's roughly what our area is. Now, what if we decided that this parallel plate capacitor was going to be square? So in other words, it's going to have a big D for a side length and a big D for a height. So in other words, we're looking at a square plate. And so in that case, we could take the square root of A, and we would end up, because D squared equals A, if we take the square root of A, we could solve for big D. And so let's go ahead and take the square root of A. 1.13, take the square root. That's going to give us D is equal to 1.06, roughly, times 10 to the, well, actually that's an odd value. Let's go ahead and let's write this in terms of 0.113 times 10 to the 8 meters squared. I don't have a smart calculator, so I can really only deal with even powers in scientific notation. Alright, so now we could take the square root of 0.113, and we end up with 0.336, roughly, times 10 to the 8 divided by 2, which is 10 to the 4, and that's meters. So if we moved this to where it was just in regular meters, we would move it 4 places to the right. That would give us 3360 meters for one side length, which is equivalent to 3.36 kilometers per side length. So essentially what we're imagining is a capacitor that has each side length in a square is going to be well over a mile. So that would be why this capacitor is not feasible. And so the answer to is this feasible would be it's not, and the reason why not is because the physical area required to make a capacitor of 1 farad with this distance of separation and this permittivity is going to be absolutely gigantic. So if you're interested to see how this equation is derived, I'll be making another video about that. If not, just remember to write this on your cheat sheet and things will go fine for you. Another thing to remember is that this is the equation to where there's an air-filled capacitor or a vacuum-filled capacitor. But the true formula has this constant K out in front, and this K is called the dielectric constant. Dielectric is going to be the material you put between these two capacitor plates. And just like I was saying down here, because E in the air is different than E in free space, well, although they're approximately the same, let's say you put plastic in between here, a certain kind of plastic, it might have a different epsilon, and so what you'd end up doing is you would look for the dielectric constant for that specific kind of plastic. And so this is the formula for all materials, whereas this is the formula for free space, or roughly the formula for an air-filled capacitor. I hope this video was helpful, and have a great day.